Alright guys, we are starting the next part of the project. We're trying to do pipelining now. So let's open the code. Visual Studio. Alright, let me get everything set up properly. Alright, everything's good. I think everything's good. Let's move this here so it's easier. Okay. I think everything is perfect. Alright, so I think we can start now. So this marks the first day of pipelining. I don't know how long it'll take, but we'll see. It's quite a process. I'm still not even done fully understanding it, but a little bit. So let's actually go through. Right? So we already have our decoder, right? Decodes the instruction based off the opcode and every other field that we need. And then we have our interpreter that actually updates register states and actually implements that like a CPU does. So we have those two. But what pipelining is we actually need to separate each step out. So if we go in here, actually I think it's in here. If we go in here, right? Is it in here? I guess it's in here, in the header file. Yeah, it's actually here at the end. Where we execute right here. So each instruction executes sequentially, but we don't want it to happen because we need to optimize our clock cycles. We don't want to overuse the clock cycles. We want to actually line them up properly so we can do it simultaneously, multiple instructions simultaneously. So that's what we need to actually implement, because as you see here, we get the instruction, so we get like the actual bits, 32 bits. Then we decode the instruction here to get the actual instruction name and all like the registers and everything. And then here's where we execute, where we put the values into the registers and actually get the register state updated. So that's like that. We actually need to split it up into five different ways now. So let me actually like show this. Let me try and show this on the notepad here. So what we need is something like this. So let's start with this. This will be our instruction fetch. Then we need to move over to our instruction decode. We need to then go into execute. Then I'm pretty sure it's memory. And then okay, I'm running out of space, but okay, I think I could just move it. Hold up. Oh, that's just the canvas ending. Okay. Alright, that's fine. Well, okay, that's bad, but okay, right back. Alright, so let's do it in like the... Let me try and map it out. So, in the situation of... Let's say this is, say this is like add I, or no, let's just do add. It'll be easier to add. So add x19 x0 and x1. I think that's a good one to do. Alright, so this will be the stage where we actually get the bits. So the bits are passed into here to find out what we're actually working with. Then here is where the bits are decoded in the instruction decode. So instruction fetch, instruction decode. So now we actually find out like what instruction it is. So like, what should I call it? Find out instruction. It's kind of hard to type right, but it's fine. You get it. All right, so and here is where we actually, the ALU takes over and the operation is actually done. Also, here's where RS1 and RS2 are read. This stage for this instruction can be skipped for this. Skip. But this final stage is where we put it all into RD, the destination register. And we don't, right now, this is kind of like what we have, but we actually, what ours would do is do it at the end here. After write back, we'd start a completely separate one. But we actually want to make it more optimized so that we can actually start doing the second one somewhere in the middle of this. So we can actually run a lot of cycles together. I think Claude had like a good, yeah, like here. So like we're running it simultaneously instead of going till the end and running. So it's kind of like that. So let's see if we can let's see if we can try and implement that today. Just something similar. All right, let's try and see. Let me just check the stream real quick. I think it looks good. I think maybe I'll shorten this a bit. We don't need it to be that big. I think here's fine. Alright, let's see. So we actually need to separate these, right? So let's go into our interpreter here. So we have the memory and we have the core. So I guess now we need to implement these separately. So because we can't pass it directly to everything, so we need to make a struct for each one. For each stage. There's no space, right? Yeah. For each stage passing from one to the next. So this stage, as we know, grabs the bit and also gets the instruction. And also like gets the program counter, so we can instantiate the program counter here, just like how we did up here. Let's just zero initialize it. I guess it's always better to, I guess that's good. Is it better to, I guess that's the value, right? It'll automatically be a 0. Let's see. Because I remember there was some problem we had earlier regarding that stuff. Was it in here? It's the string. Unknown. I mean, I guess that's fine. I guess that's fine. Yeah, so you want to actually separate this out. So starting with the instruction fetch, instruction decode, which grabs the program counter, also grabs the bits. So that's going to be an unsigned int as well. And what should we call it? Just like the raw bits, I guess. We'll call it raw bits. Or, nah, that's too long. Let's just call it bits. So that's like the actual bits that we're getting for the instruction. So the 32-bit string that we're getting. And we want to actually like make sure that if we have a stall, I haven't actually gotten into the stalling, I haven't explained it yet, but basically if we're grabbing a value that's in a destination register that hasn't been updated yet, we want to have a couple stalls, like a bubble essentially. So we'll call it bubble. We'll set that as true. So essentially for stalling here, we'll automatically have this skip, implement the bubble there so we can skip and wait until we have the destination register properly updated. Now we can make the structure the rest of the stuff. So the next one would be moving from instruction decode to execute. So what would we need in that? So yeah, I saw it, so looks nice. So instruction decode to execute. So we want to actually find out what the instruction is. And we'll also need the, well, we probably need to call the decode instruction now here. And we'll call it instruction because I believe from earlier, decode instruction was to get the actual instruction name here. So that should work if we have a decoded instruction and call that as a thing. So yeah, our program counter is obviously needed still here because we need to pass that in. Oops. Alright, so like that. And what else? So we need RS1 and RS2 values. We need to keep those values in because that's what we're taking. And also, I know some instructions have RS3 as well. Like the ones here have RS3 somewhere. Let me check. I think it's fadd.s. No, it's something else. fmadd, I think. Where is it? fmadd. Yeah. They have an RS3 value, so we also need to store RS3 state as well. So 5 versions and DMs. It looks pretty nice. So you're going for more like a blocky style game. I see. Pretty good, man. Pretty good. So you want to store rs1. And also store rs2 as well, and rs3. So we want to essentially get those as well, passing those over. Level 10 is done, but I'll have to screenshot. Alright, man. You'll be right back? Alright. Take your time, you can take your time. Alright, these will be zero initialized. Okay, so what else? Is there any other like values we're reading? I mean, not really, right? Not necessarily. It's kind of interesting. How much do I have? I have a good amount here. I think I can show an example of the bubble. I think I kind of want to right now. Give me a second. Alright, yeah. Alright, let's go here. I want to do an example of the bubble, right? So let's just take our one from earlier. Right, perhaps like earlier we had the add instruction, right? So we had like add x19, x0, x1, right? So essentially we have our instruction fetch, instruction decode. Let me just put these all in different brackets so it's easier, in different squares. Then we have our execute, also our mem, and we have to write back the result in destination register. Then let's say we have something like a subtraction instruction, like a sub x2. Let's say it takes the value from x19 and also subtracts the x1 value, or not x1, probably let's do x3. Let me go back. Let's do x3. So we have x3, yeah. So yeah, it's taking x19 value from add. That's the finished computing result. So we want to pipeline this, right? So we want this to execute with this, along with this. But we don't want a data hazard. So we don't want it to use the result of x19 before it ends up writing back. Or else we'll grab a random garbage value, or the old value that we don't want. We want it to actually write back here first and then grab that. So essentially, we can start the instruction fetch right after this starts, like right after it. And we can also do the decode as well. So that we can do the decode as well. But here's where we kind of want some bubbles here. We want to stall here, a couple stalls here. Maybe 3. We wanted to finish writing back first, and then we can implement. Stall, and then we can implement. Level 10s and DMs. Alright, I'll check it in a second. I'm just trying to map this out real quick so I can understand. So we have that, and after that we want to do, like literally right after that, we want to do mem and write back. I don't have enough space, but I think you get it. So we need these stalls so that it doesn't grab the value before it writes back. So that makes sense. But after these 2 or 3 stalls, depending on the timeline, we can actually then grab it in memory or do the write back. 69 and 70 subs? Yo, I appreciate it, Benz. Appreciate it, man. Finally hit that 70 subs milestone. We've been growing kind of fast, not gonna lie. Like lately. It's been pretty nice. I think like 2 weeks ago I was at like 40 or something. So I think we were growing pretty well. So yeah, that's basically the map out of this. So that's why we want to implement bubbles to actually stall the value. So let's see. Is there any other value we need in our struct here that we need to store? So we're going from instruction decode to execute. Usually it'd read values in the source registers here. We don't need the destination register. We don't need the immediate values yet either, do we? Immediates would be more for the other stage, probably. Yeah, probably, yeah, not immediate. I think that's it. Because I think the rest are just immediate. So I think, and we can just end off with the bubble. So that's true. And let's see. I think that's it. So we can move on to the next struct. The next struct will be execute, moving into mem. So like that. And what exactly do we need? Oh, also wait, is this? It would be unsigned, right? I think it would be unsigned because that's what we're getting from the bits. We don't want to change it till later. That's in the actual implementation. Hey, what's up, Blackbeard? That's a W name. If that's from, is that from the real life pirate or from One Piece? If that's from One Piece, that's a W. But how you doing, man? How you doing? Alright, execute. Alright, so in this stage, for execute memory, you can take a look what it does here in our thing. Right, yeah. Oh yeah, that's the ALU part. So we're actually using the values from RS1, RS2, RS3. We're actually like implementing the instruction. So we would probably need this again, because you want the instruction type. I really don't know if this is the right implementation, but we'll check after. I just want to get something done here, just to see. Hopefully we're thinking about it right. Hopefully. I'm just an aspiring developer. What is the pipeline they're building? Is it for a game engine or something else? This is for my CPU emulator. This is mimicking risc-v architecture. I have the decoder written out, so it takes in a 32-bit string and then decodes the right assembly instruction. And then we have the interpreter built out, which is actually putting it all into registers, updating register state, and actually computing values properly. So it kind of mimics like CPU memory, the registers. And now we're actually getting pipelining, which is allowing the instructions to be executed together. Instead of waiting for one instruction to be done, we can start doing the second instruction as soon as the first part of the first instruction is done, which is kind of what I have here in my diagram. The current implementation I have right now, we'd have like this. We'd have this part running, and immediately after that's done running, the rest starts from here. But we need to make it so as soon as this first part is done, we can start running this immediately. So it optimizes CPU cycles. So that's basically what we're doing right now. Alright, so for execute to memory, so we need the decoder instruction. I guess we'd also need like a Would we need the RS1? Appreciate you, Blackbeard. Appreciate you, man. Would we need RS1? Okay, let's say, okay. So we have the execute here. I guess... Let me take a look at my notes again real quick. Instruction decode, figure out what the bits mean, may further check func3, func5, all those values, yeah. Performing the computation, the ALU takes over, does its job, yeah. Okay, so I guess, yeah, so in execute we'd already like use these values up, so we'd want the ending computation of this, so I guess we can call that like, we call that like ALU. Like ALU result. Something like that, wait. How did I format these? I guess just like that. So it wants to grab the ALU result, right? And just zero initialize that. This is the result of the computation done between any of these registers stored in that. What else? Okay, let's think. So most instructions do computations on these, on RS1, RS2. Some do a computation on immediate though, so. But let me see. Well, let's go back to our decode instruction. I mean, I guess RS1's already here, right? So, I guess I'll ask Cloud about that. Like, if we don't even need these variables at all, since it's already, we're grabbing our struct, right? So, I wonder if we actually need them. Alright, so the ALU result, that's good. Immediate. Actually, let's ask right now, to be honest. Let's just ask right now, see what's going on. Alright, so I have these two structs to present this pipeline. I was wondering about the need to even instantiate the source registers, because we already have them initialized. Alright, let's see what he says. She needs classes as you're using C++ instead of C. I mean, you can use structs in C++ too. Really, the only difference between like structs and classes is structs, the data is just public, classes are private. I'm more comfortable with structs for now, but I might change the classes later if I need to. But for now, I think structs work just perfectly fine for me. Because I'm still pretty new to C++, so... Like, I know how to use classes, but like, it might be a bit too complicated to use it right now. The question, there's an important distinction though. Instar RS1 decode instruction is a register number, which register 031, RS1 IDX should be the register value. Oh, yeah, okay. Oh yeah, it's gonna be separate, yeah. By the time you get to execute, use the forwarded values, not the register numbers. Because the forwarding, you might not even use a register file value directly. You might substitute a value forwarded from a later pipeline. Okay. Just don't go too deep into memory management in C++ or start balding because of anxiety. Yeah, that's true. Hey, we'll see, we'll see. Right now, all I know is pointers, references, and smart pointers. That's pretty much all I know so far. Okay, so one question: do we need R3? I mean, yeah, we do. Though. I'm from the USA. Okay, I guess it's probably better to make a distinction because I don't want to get confused. So I'm gonna call this rs1 value and do the same with the rest of these. So it'll be better to distinguish because if they're gonna be the same thing like this, I don't want to get confused and accidentally write like inst.rs1 when I need to write that. So I'll deliberately make it value with the suffix there at the end there, so that'll make it better. From Bangladesh, country south of India. Nice, man, nice. My parents were born in India, so, but I was born here, so I don't know too much about India, to be honest. I just visit once in a while. Okay, failure result. Then I guess we would need it. We would need the. Okay, let me create one more time. Wait, let's think. The difference with this is that we're accessing rs1 value, but for like func3, func7, we're not really accessing a value, it's just a bit, so I think we don't need them. But here though, let's check. Immediate would also be just a value, but that value is already instantiated itself. We're not accessing a register value. Let's see, load byte, destination, immediate. Yeah, here's the difference. We need to access the value of rs2 here within the register and store that into the offset value of rs1. So we would need like a rs2 here, I believe. Let me just read this again. Stop, mem register, execute, ALU takes over, does job. The ALU result that we need to be stored into memory now. If the instruction is a load, CPU takes the address calculated in X stage, goes out to the RAM, increases data. If it's a store, then takes a value from a register and pushes that out to RAM. So we do need the value from register. Damn, bro, you look like a computer engineer. I've seen horrible things in your GitHub profile picture. Yeah, yeah. The crazy thing is I'm not even doing like computer engineering in my college. I just got interested in that stuff, so I'm trying to pivot into that. And yeah, my repo is there for the risc-v emulator. We got like 2 stars on it right now, and I'm pretty happy with that. Yeah. So we're doing the rs2 value since we're taking that value and storing that into the offset. What else do we need? I guess that's it. That's the only off case, right? That's really the only off case where we store from our register into a value. Registers to memory, so I guess we just end off with the bubble again. Okay, that's done. Okay, what's next? Now we need the final stage, which should be mem to write back. We also need our type here to grab all the values. What else? Okay, so writing back is just writing it back to the register, the destination register. So what exactly do we need? So we also still need the ALU result, I believe. So we can just copy that from here, because the ALU result is what we're actually storing into the destination register. What else? I have to just read it right. No, write back, say the final result. Read it right. Data memory. Mem slash write back register now holds either the data pulled from memory or the result passed from the ALU. So we have the result passed from the ALU. How do we get the data pulled from memory? I guess we need a new value for that, right? Let's see. So it would be something like because we need the memory value from what we did here. Same thing here. We need the memory value. We're storing that. We're getting that stored from rs2. So I guess we'll call it something new. I'll just call it memoried, I guess. Call it memoried. And then the bubble. Oh, not that. I have the bubble. And then we have the bubble. Alright, so I think that's good. I'm gonna see if Claude thinks that's fine. Let's see what Claude says. Good structure, the pipeline registers look correct and well thought out. A few observations. Bubble flag is a good design choice. It lets you insert knobs into the pipeline for stalls without corrupting real instruction data. Yeah, that's what I was going for. X to mem, keeping RC value correct. You need this for the store instruction. Yep. Mem write back. Having both ALU result and memory is correct. The write back stage needs to choose between the two depending on whether it's a load instruction or arithmetic instruction. One thing missing: PC program counter in execute to mem and mem write back. Carry PC through the X would drop it after that. Oh, you're right. I totally forgot about that. Yeah. Let's get the PC value in each of these. I totally forgot. Okay. You'll need an xmem for branch resolution and potentially in mem write back for debugging / exceptions. Okay. It's good to have it. Question before you implement the pipeline loop. Are you planning to handle the pipeline stages in your run function? Project stage in reverse order each cycle. Write back first, then mem. I actually don't know why reverse order matters. Let's think though. Reverse order. Okay. So what he means is like calling right back first, calling them, moving that way. It's the wait. To be honest, I don't really know. Instruction fetch fetches instruction, writes to instruction fetch, instruction decode, read from instruction fetch, instruction decode, but you just overrode it in step 1. Oh, okay. Okay, wait. If you're reading the new value that was just written in the cycle, not the value from the previous cycle, every stage would be consuming data that was produced in the same cycle rather than the previous cycle, meaning all stages would effectively be operating on the same instructions simultaneously. Hey Lucy, what's up? How are you doing? That's good, that's good. Okay, so I guess because it moves like together, I guess, like sequentially, it would be updating it without ever reading the right values. So we want to do from reverse. Yup, EXO. Welcome back. I didn't see the leak, let me check. Looks pretty good. Looks pretty good, man. Okay, okay, that makes sense to me now. Did you have any problems with my actual like thing though? No, we already covered it. So now how do we move these to them? I guess in here, because what we were doing earlier is using our execute here. We were using our execute function in here, right? So we actually want to move it now. I'm gonna move these over. So now we'll be fine. And we want to implement it in here. So let's call it like first one's IFID, right? So and I noticed we have a reference. Probably be better to have a reference of that. What should I call it? Let's call it like IFID. IFID Reg probably is probably the best name for that. Next is the IDX. edge. And we want to get the last one right back. Kind of like that. So we have one state after the another. But this is just reading, so I guess we need also... do we need another set of these for the next values, or let's see. Exactly right, this is a double buffering problem. You need two sets of pipeline registers, the current value is being read, and this cycle's next. Okay, so let's get this in there. Oh, wait. Okay, I just want to make a distinction here real quick. Just grab one of these probably, and I just want to know the distinction of why we can't. Different ownership semantics. From outside, core doesn't own it, it just borrows it for the duration of the run. Reference makes sense because memory lives there. Somewhere else in main, and multiple cores could share it. Okay, I guess that makes sense. So they're actual values. So we wouldn't make these references because they're actually owned in there. But this part isn't owned for the memory, so okay, let's make our next part. So I guess I'll just copy these and just call the next one. Right back. And then in our void core, in our actual core, where's our core at? Here. Okay, inside here, inside. It would be out here in this core instead of having what we had before. Let's see. That should be fine. But instead of here, we want this to be changed. So I guess comment it out for now. Just keep it on the bottom there just in case we need it again. Okay, so reverse, we need in reverse order, right? So how would we call these? So while it's not halted, I guess we need to make functions for how they're actually implemented right now, so we can actually implement it in here. So I guess it's forward declaration. I'm in here. Forward declare that. Or should we make a new, just a new function itself in here? Hey, what's up, KZ Mans? How you doing, bro? Welcome back. Wait. I guess we need a function. So yeah, this is what I was expecting, but we actually need to write the function now. You good? Nice, man, nice. It's going pretty good here. We're trying to implement pipelining now. Which is the next stage of my project here, so it's completely new implementation. So yeah, I guess we can separate different functions for each. I guess, is it lowercase capital or? Well, first we need to actually forward declaration. And I guess I'd take the memory. It actually needs memory, so because it'd essentially be the same as this, essentially just taking the value of the memory address and then computing from there. All right, let's start with that at least. Memory again. Why is this not working? Wait. Oh, it's working now. Okay. I was about to say, I was so confused. All right, so now it's good. So essentially for the fetch stage, right? Let's look at our thing again. So we're grabbing the bits, right? So we need to grab the actual instruction. So it would essentially just be the same as this part here down here. So like raw instruction, literally just down there, word for word. So just be that. So that's fine. Next, I want to take a look at my notes real quick. Trying to fetch, grabbing 32-bit chunk of binary data. Looks at PC, tells the memory address, and goes to that address in instruction memory, copies the 32-bit word, and pulls it into CPU, updates PC before cyclines. Okay. Well, I guess it's incrementing PC by 4. And there's gonna be another step. I think we're gonna have to pass it to the next function. So now it'd be, that's where we had those variables from before. I think it's like next ID reg. I think that's how we wrote it, right? Let me check. Yeah. So these are just normal and then registers, and this is next and then registers. And then raw instruction, calling that from earlier. Or no, so it wouldn't be raw instruction. I guess just that, right? And then this would be raw structure here. Wait. We'll take a look at what's going on here. Let me just finish implementing the rest of this. So we're getting the raw instruction. I wonder why this doesn't work. Wait. It's not match parameter. Interesting. To be honest, I don't really know, but we'll see. We'll check right now. Equal sign for next. Let's see if it's something dumb or something. What's next? It's an IFID struct, not a. Send it to. Is it? Wait, what? Oh, wait, yeah, okay. I see. Right, yeah, it's part of the struct. Yeah, it's a struct that we initialize. That's what I messed up for. So we need to access a value within that then. which would be the bits, I believe. Right? I think for the raw instruction, so bits. I think. Let's see. Yeah, the bits, yeah. What do you say? Store PC before advancing. Yeah, I was gonna store the PC. I guess I just forgot for a second. Yeah, so accessing any value within this has to be dot in the variable. I forgot about that. That's why I wasn't working. And then we want to get the bubble as well. I think we initialize it as bubble. Yeah, just bubble. And set that to false. Yeah, I think that's good. Oh wait, it's not reg. Wait. Wait, what? I think mine should be right. Mine's like this, so that's probably why. I think this is good. This should represent the fetch part properly. I think for example, right. Now write decode stage. Yes, I will write decode stage now. Coding, figures, and func search registers and media values. We also check func 7. Okay. So not this. We need to first check if it's a bubble. So if the IFID, oops, not capital. If the IFID not its bubble. We already have bubble, just like that. It's not its bubble. Got confused for a second. Should just be bubble. And why is that not working? Oh yeah, that's because we haven't instantiated. In here. Alright, that should be good now. Alright. And we want to set the bubble as true. Okay, like, not gonna lie, pipelining is kind of confusing in a way, to be honest. Oh yeah, we don't want it to go further to return. Pipelining is kind of confusing in a way, not gonna lie. But if it's not a bubble, we continue on. and we need our decoded instruction now. So let's look at our decoded instruction. So now we need to actually make one and get our function running. Yeah, this function here. And it takes in the unsigned bit value. And what do we call it? I guess the bits. We want to get the actual bits of that. We want to get the actual bits, and then now we need to actually grab the rs1 and rs2 values that we have. So let's get those into. And let's call it rs1. Let's just call it the same thing as here, rs1 value. And that's going to be equal to reading the register, as we usually do, of our rs1 value. And we have to do the same for rs2 and rs3. And I'll separate this out since it's only used for a floating point, so I'll just have it here separately so I know if I'm coming back to this. It's not rs3. And that's for floating point only, since no regular instruction uses rs3. Oh wait, well this would be floating point reg though. And wait, let me check the implementation again. They're all going to be floating point registers, rs1 and rs2, so we'd also need. Let me just copy these. What did I do? These to be like this, so this would represent floating point now, and I think that's good. But the variables, let's call it f value. I suck at naming variables, not even gonna lie. Variable naming is actually really hard. rs1 f value, alright, let's just call it that, that's fine. And we have everything, but now we need to pass the value over to the next stage, the execute stage, I believe. The execute stage, so we need to pass all of it over, so let's see. Make program counter. see, counter. So we're making that the current one. Let's see. We need the RS1, RS2 values, so all those stuff. Well, I guess it'd be kind of confusing, right? If we did that, it would be kind of confusing to know for sure. So I guess we can call them different stuff. Let me see. Because that one's like that, so I guess we can call these different names. So it's easier to know. And then that would be better for that. Rename them RS2 and RS3 respectively. And then this will also just be that. I guess now it's better to distinguish. So we know that we're changing the value of the struct that we access with the actual value that we made appear. Well, do we really need the extra? I guess we can just call it F value. That'll be easier to write out. Alright, next. Essentially it's the same. Just the same. But we're just doing this. And also this. Same here. Reg, that'll be rs1 value again. Because it would just be that rs1 value, right? Would we need a new values for these, like in the struct? I mean, it is technically unsigned int still. So let me see. I'll just write this out and then see with Claude, but this one will be f value here. So rs2, this will be rs3. And then what else? I think that's good. Bubble. Dot bubble. And that'll be false. I think that's good. Let's check. Let's also check it with the struct as well, by the way. All the structs so far. Let's see. Structure overall, fusions to address. Floating point, register values overriding. Oh yeah, they are overriding, yeah. Okay. Yeah, so that would be a pretty big mistake here. So let's actually add them to the struct. So we'll just probably name it like this. Probably do it like that. And we'll call it like that. Yeah, that should be better. So now the values aren't overwriting. Should be pretty straightforward there. And okay, I guess, okay, what are the other issues that he said that we have? Yeah, the overwriting issues, issue 2, read returns float, not untyped integer. Right. Let me go back to the interpreter. Oh, where is it? Should be in core, right? Yeah, float read f reg, that's my bad. So all these need to be float. Yeah. Same with these in here. In our struct. Okay, that's good. Everything's good there. Float values, bubble. Okay, that's all good. And now we can address the final issue, always reading both integer and floating point registers. You're reading floating point registers even for integer instructions. Not wrong, just wasteful. You can check inst.type. Okay, we'll check inst.type. So we'll just make a simple, it's like a simple if statement. So if our inst.type yeah, but there's a lot of inst.types though, I'm not gonna lie. How could we go with this? So I have inst.type. I don't want to go through every single one. So how exactly can we do that? How many are there? Actually, not a lot though. There's actually not a lot. It's like just a couple, but that's still a lot of checks though. So let's see if it's even worth it, like distinguishing. There's a lot of inst types, so it might be hard to implement that. Yeah, so it's just fine to read it. Doesn't really matter. Cost is minimal and the code seems clean. Yeah, there's no point in making an if statement for that. It just adds so much extra work for that to check everything. Just have them instantiated, that's fine. Okay. I think it's 12:30, so maybe one more. Maybe we'll do one more function for today. Maybe. We'll see how it goes. If I get too confused, I'll just like stop and pick it up tomorrow. Wood core, and this will be the execute stage. And does it also need the memory? Let's go to here. Instantiate in here. So that's good now. And in here is where we need to change now implement stuff. So execute stage is where the ALU actually does the work. The ALU does the brunt of the work. So ALU takes over and does its job like we mentioned up there in the data path / control section. So execute / memory register now has a computational result or memory address. I guess we still need to do the bubble check, right? So let's just get this up here. We also need to grab these stuff. Or wait. It should be in there from the last time. We don't need to reinstantiate it. It should be there from the last one since we're in the same struct. Should be there. And the ALU result is what I called it, right? Yeah, ALU result. I'm gonna separate these real quick. ALU result, and set that equal to I guess just zero initializer for now, I think, right? I guess we'd also need a float for that too. Let's call it like F result. Zero initialize that. Or how does, wait, zero initializing for floats? I don't know how that works. I guess Cloud will point it out. I think I should actually instantiate. I don't know though. Let's just check with Cloud later. Now here though. What exactly do we need here? Let's just check if everything's good so far. code. Let's see. Okay, if ID, yeah, wait, wrong register check. Checking that bubble should be, oh wait, oh yeah, you're right. Forgot to change it. Forgot to change it after here. It should be X, ID X. Yeah, that's good now. On the switch statement question, yes, your existing execute function already has all the calculation logic. Case approaches the refactor to the calculation logic is separated from the memory / write back side effects. So yeah, this is our execute switch we had before. So how do we want to actually refactor so it doesn't actually do everything. Damn, are we gonna need a huge refactor here? Damn. Wait, so that's gonna be a hassle, not gonna lie. That's gonna be a lot of work right now. Alright, I think we'll just end the stream for today, to be honest. The next part's gonna be a lot of work. I have to rewrite. I don't know if it's like a rewrite, but it's like refactoring this in a way that it doesn't write to the register. It only calculates the result of it and stores it in the writing to registers in a later part. So I guess it won't be too bad. We just have to split this up. But yeah, we can continue that tomorrow. I think today was a W stream. It was really confusing, but I think we got through it. And yeah, we'll continue out tomorrow.